Okay, so this video is about classification of finitely generated modules over principal ideal domain. It will be explained what it is, and some applications to structure of finitely generated abelian groups, and also, maybe surprisingly, to the Jordan canonical form of endomorphisms of vector spaces over algebraically closed fields. So the theory we have done today will permit us to give a very easy proof of the existence of this Jordan normal form. If you want to see details of what I do here, you can look at this text by Lenny Thalman, which is called Modules and Categories, and you go to chapter 3. Okay, so finitely generated modules. This has already been explained by Arno. But I would like to say one more thing. So for R, a ring, and M, an R module. So we know what it means that M is finitely generated. It means, for example, that M has a subset, a finite subset that generates it. Have we seen other? That is what we have seen. So, but I would like to. I would like to give a slightly different description of this. It's finitely generated. Finitely generated. If and only if. So maybe here. If and only if there exists an n in n and a surjective morphism from the free module Rn to this M, right? This double-headed arrow means surjective. And how do you go in this direction? Well, that's easy, because the FEI, where the EIs, I1 lesser equal I lesser equal n, and these EIs are the natural basis vectors for Rn. They generate M, and that is a finite set. And if I want to go this way, I take a finite set of generators, so let M1 up to Mn in M be generators, be such that together as a set, if I generate the R module with it, that is M, then take F from Rn to M, the map, the unique map that has the property that f of EI is this MI. Right? The free module, to give a map from a free module is just to give the images of the basis vectors, and so then this will be a surjective map because these MIs generate M, and that's it. So the thing to remember is, if you have a finitely generated module, you can find a surjective map from a R to the n for some n. Okay, so then I come to the next word that I have to explain, principal ideal domain. So, definition, a ring, I will remind you of this, D is called a principal ideal domain if, so first it has to be commutative, D is commutative, 2, D is an integral domain. And let me remind you what that is. This means that D is not the zero ring, so the element 1 in D is not equal to 0. And moreover, if a product of two elements is 0, then at least one of them is 0. And thirdly, that is the principal thing, principal ideal. For every I in D an ideal, there exists an X in R in D such that I is R times X and we will also denote this by x between parentheses. Right? So every ideal can be generated by one element. So these three conditions are what it takes for a ring to be the principal ideal domain. And we know quite a few examples of that. So this is a class of rings that is slightly more complicated than fields, but not really terribly much so. So the 0th example, every fields are principal ideal domains. Yeah, because, well, you can check it is commutative, a field, otherwise it would not be called a field. A field is also non-zero, it is an integral domain actually. Every non-zero element has even an inverse. And a field has only very few ideals, right? You have the zero ideal and the whole field itself. Those are the two zero ideals, and they are generated by 0 and 1 respectively. So fields are PIDs, but that is of course not the reason why this notion was invented. It was invented for some more interesting examples. So Z is a principal ideal domain. Well, let's check the properties. Z is commutative. If a product, it is not the zero ring, and if a product of two integers is 0, then one of them was 0 at least. And every ideal is principal. And this, I suppose you have seen a proof of. So let me prove that. Let I in Z be an ideal. We want to have a generator. But a generator, you can get it by looking at the smallest positive element of I, if that exists. So if I is 0, then okay, right? It is generated by one element. So suppose I is not 0, then I has non-zero elements, and if it cannot not only have negative non-zero elements because it is an ideal, it is closed under inversion for the addition. So then there are positive elements, and then you can take the smallest positive element, right? Let n be the minimum of I minus 0 intersected with n with the natural numbers, right? We are in Z, so here I take the smallest positive element of I, and this exists because, well, I told you. Then I is Z times n, and in other words, this is also denoted by that. And how do you prove this? This you do by division with remainder. You take any element of I, you divide by remainder. You do division with remainder by n, so you write it as sometime a multiple of n plus a remainder. That remainder is in I, but it is strictly between 0, it is greater or equal 0 and less than n. And then, yeah, the minimality here says that remainder should be 0. So all the elements of I are multiples of n. Right? So that is the proof that Z is an integral, is a principal ideal domain. And you see that it uses actually the fact that Z is even slightly better. Z is Euclidean. I used the division with remainder. Well, the same proof works for the next case. If I take a polynomial ring in one variable with k a field, I also have division with remainder. This is also a Euclidean. It's Euclidean. Euclidean means you can do division with remainder for some measure of how small elements are. And for Z you use the absolute value, here you use the degree. So, and therefore a PID. So the fact that it is commutative is clear. It is an integral domain. You have just to show that every ideal is generated by one element. Well, again, the zero ideal is generated by 0, or by 0 elements if you like. And a non-zero ideal has elements of positive degree, and you take an element of smallest degree, and that will generate your ideal. The same argument. Okay, so that's very good. Now you might wonder that if every every principal ideal domain is Euclidean, but that is not true. I looked up an example for you. Zx mod x squared minus x plus 5 is a p-idea. It's a principal ideal domain, but not Euclidean. So you cannot find a function from this ring minus its 0 element to the natural number, say, for which you can make a division with remainder. So there are cases that are not of that case. And if you do examples, well, you can also do a non-example. So it is really quite, this is not a p-idea. For example, the ideal generated by x and y, so this is the notation for an ideal generated by two elements, is not principal, not generated by one element. And how do you prove that? Well, if you have, so you could do that. So if f, the ideal generated by f would be this thing, if you could generate it with one element, then this x is an element in the ideal, so then x is g times f for some g, right? But this is also, and also y is h times f for some h. But this ring, we know it is a unique factorization domain, right? We know that. This you learn. So, and x is actually a prime element. So if x is g times f, then f has to be a divisor of x. And so f is either a constant, f is in k star, but that you cannot have with an element in this ideal, so this is out. And so f is a constant, a non-zero constant times x. But then you cannot have that this divides y, right? But at the same time, f should be of this shape, and that is not possible, right? So a polynomial ring in two variables over a field is already not a principal ideal domain. Okay, good. Well, in principal ideal domains, you have the same construction as in the integers of a greatest common divisor and least common multiples and such things. So remark, let D be a p-idea, principal ideal domain, for A and B in D. Any D in D with so that the ideal that it generates is the ideal generated by A and B. And of course, for every A and B, such D do exist because every ideal is principal. Any such D is called a greatest common divisor of A and B. And this is also the notation for it. And it is unique up to units. So even in the integers you can have minus a number generates the same ideal as the number you started with. So unique up to the units, right? This is the D, well, the U in D, for which there exists a V in D with U times V is 1, right? The ones that have an inverse for the multiplication. This is the unit group of this domain. So this notion of GCD, greatest common divisor, is unique up to these units. And depending on which ring you are, these units will be, what they are, right? So for example, in the integers, the only integers that have a multiplicative inverse are 1 and minus 1. But if I take this one, the units in the polynomial ring, well, then you see that you get the constant non-zero polynomials, right? Polynomials of positive degree can only have multiples that have even a higher degree. Okay, so we have greatest common divisors, and I will recall you some facts also. D is a PID. Well then, D is a unique factorization domain. This is not completely trivial, but to prove it, you use the fact that you have GCDs. So to have a unique factorization domain means that every element can be written as a product of prime elements. Every non-zero element can be written as a unit times a product of prime elements. So for every x in D with a 0 left out, there are, well, x is a unit times P1 to the E1 up to PR to the ER with U in the units. The PI are prime elements, primes, and distinct, say, to make it unique. So distinct means that for every I not equal to J, the ideal generated by PI is not the ideal generated by PJ. And the EIs say they are integers greater than 0. And then that the way to write this is unique up to permutation of these primes, actually, and up to units that, because these generators you can for the ideal you can have other generators up to unit things. So the crucial property here that you must have for this unique factorization is that every irreducible element is a prime element. And that is something that you have seen for the integers. If you have seen why in the integers you have unique factorization into primes, then you can use the same arguments to do it here. Okay, so then I come to a theorem, and let's say that's theorem 1, and I hope I can remember the numbering. Let D be a PID, a principal ideal domain, and N a natural number, and M a submodule of D to the N, a submodule. Then we claim that M is free. We have to prove M is free. That is what the theorem says. And okay, so how am I doing on time?
12 minutes.
Past or still left?
12 minutes left.
Ooh, okay, good. Well, then I need two movies. Okay, but I'll do it. So the proof is by induction on N. Induction on N. And let's start with N very small. For N is 0, clear, because if you take 0, you get the 0 module, and any submodule is also the 0 module, and that is free of rank 0. For N equals 1, well, then we have M inside D is an ideal, right? If I am in D to the 1, then D to the 1 is D. And this is an ideal, and precisely the fact that every ideal is principal gives me a generator for the ideal. And so 0 is isomorphic to R to the 0, and for every D not equal to 0, the ideal is isomorphic to R, because I can send X in R to X times D. This is a surjective map by definition of the ideal, and it is injective because R is a domain and D is non-zero. So this is a bijection, right? And so that does it for this. And now we are going to use the induction hypothesis, right? So now let N be greater 1 and assume that every submodule of D to the N minus 1 is free. And we are going to prove that any submodule of D to the N is free. Okay, for that we look at the following. We consider this. D to the N, we can map it to D. And we do that by projection on the nth coordinate. So this map sends x1 up to xn to xn. And this is a surjective map, of course. Yeah. And the kernel is d to the n minus 1. Right? Which I map here, and x goes to x comma 0. I put a 0 on the last coordinate, and then I have the kernel of that map. And here I have m inside this d to the n. And when I map it to d, well, it may not be everything, but it is a submodule of d. So here I get d times d, say, right? For some d, and this is subjects to that. And the kernel is m intersected d to the n minus 1 inside here. But now, this is free. So you take a basis, so the claim is, if you take here, this is free, and you can say, well, let m1 up to mr be a basis of this intersection. And then you can say, well, if d is 0, then this m1 up to mr is a basis of m, because m is equal to this intersection in that case. And if d is not 0, then this m1 up to mr together with an m, so I can say, well, I take an m in here whose image is d. This is a basis for m. And why? Well, because if I have any element of m, I can map it here. There it becomes a multiple of d. That coefficient I use as a coefficient for m. So if I subtract that number of times m from my element, the image is 0, but then it means that difference is in this intersection, and then I can express that as a linear combination here, and the uniqueness is also clear if you think about it.
So maybe not all the viewers have seen what an exact sequence is.
But I don't use it. It is just a subset. Yeah. So it is a map. Yeah, it is true. But that is the subject of something for tomorrow. If you want to know more about exact sequences, you have to wait a little bit. But I claim that here you don't care. I also, Arno talked about kernels and I did not complain. So, okay, good. So I think there are a few more minutes.
7 minutes.
7 minutes. Okay, but then I can still go a bit further. So in a PID, you have the nice thing that every submodule of a free module is free. And I already showed to you that the polynomial ring in 2 variables over the field is not a PID, and I can also give you an example that actually here, you see, this is a free module of rank 1, right, over that ring, and I took a submodule. And what I show here is that you cannot generate this with one element. Yeah, but I can also say, if you take 2 elements here for every f and g in this xy, well, you can generate this with 2 elements, namely x and y. But if you take elements in here, they are never independent over this ring, because you have always the relation that g times f minus f times g is 0. Right? So that means that you can never find a basis in there, because if you try to use one element, I already told you cannot, and if you want to use more than one element, you get into this trouble. So it is very peculiar for principal ideal domains that you have this result. And actually, it's even true for free modules of arbitrary rank. It is even true if I take this into d to a big direct sum. It's still true with transfinite induction, if you like. Okay, good. Then in the remaining few minutes I do another theorem, and that is then theorem 2. Okay, let D be a PID. F0, F1 inside F0 an inclusion of free D modules of finite free of finite rank. The rank is the n for which f0 is d to the n, say, right? That so you could say free finitely generated d modules. This is of d to the something, and that is d to the something, and both somethings are natural numbers. Okay. What I claim is that then there exists a basis, or bases, it is plural, say E1 up to ER0 of F0, F1 up to FR1 of F1, and elements D1 up to DR1 in D minus 0, well that follows by itself, such that F for every I in 1 up to R1, you have that the Fi, so the ith basis vector for F1 is the Di times the ith basis vector for F0. And in particular, this means R1 is less or equal than R0, because I have at least as many EIs as that I have FIs. Okay, so this is a very nice theorem, and the proof goes as follows. So here I will just do some hand waving, but it is an algorithmic proof. So you take, let E1 up to ER0 prime and F1 up to FR1 prime, everything be any basis of F0 and F1. Then you have, that gives a matrix, gives A in matrix, say, what do I want to do? I want to express these on terms of that. So R1 times R0 comma D, such that for every J, I would like to say that I want to write the F as a combination of the E's, right? The module of the F's is contained in that. So Fj is sum A, I, J, E, I, right? And here you sum over the I. That you can do. And then you can, so this is a matrix. Oh. And now you can do row and column operations, just like in linear algebra, but now with coefficients in D, and you can go to a matrix that is like this, D1 up to, well, maybe this matrix is a bit higher than it is wide, DR1, and then here, if you go on, you have zeros. And from this, that is how you get it, right? That is the, okay, and I think time is up.
1 minute.
1 minute. Well, okay, so maybe, yeah, well, okay, but let's stop it anyway.
Okay.